OK. So you may have heard somewhere that your computer is all about zeros and ones. And so as this slide suggests, we're now going to learn what those zeros and ones actually mean. So first, we need to look at why 0 and 1. I mean, we have a bunch of other digits like 3 and 7, but our computer instead decides to use only zeros and ones. So let's start with a question. The question is, do you like cats? I know everyone's answer is yes, but there really are only two possible answers to this question, either yes or no. So this is what's called a binary state. There are two different states we can have. We can like cats, yes, I do like cats, or we can not like cats. So anything that can be expressed using one or two states can be expressed using binary. So we could represent an answer of yes, I like cats with the number 1. We can represent an answer of no, I do not like cats, which makes me sad, with a number 0. So similarly, we might use something like true or false, or something more concrete, like is this light on or off? So inside of our computer, we might represent a 1 by flipping something on. On the other hand, we can represent a 0 by flipping something off. So this is what we mean when we say something is binary. There are just two possible values that it can have. So before we delve more into binary, let's first remember, so instead, a different question is something like this. So how much do you like cats? Suddenly, this is not a binary question anymore. There are multiple answers to this question. It could be I like them a lot, I don't like them at all, I kind of like them, I really love them. So suddenly, this 1 or a 0 is not enough. Instead, we need to somehow be able to express this whole range of values, but still only using a 0 or a 1. So as far as our computer is concerned, we can only represent something as on or off. So before we do that, let's first take a look at how we are probably used to representing numbers. So in grade school, when we were learning to count, and we learned how to write down numbers like 123, we may have used these things here, these base 10 blocks, I think they're called. And basically, each of these small cubes represents something in the ones place. One of these columns is something in the tens place. One of these big rectangles is something in the hundreds place, and so on. And so we learned that when we write down a number with different digits, we write down something like this. So each of the digits in a number is a different place. We have the ones place, the tens place, the hundreds place. So if we write down the number 1, 2, 3, what that is equal to is 1 times 100 plus 2 times 10 plus 3 times 1. Right? We're all used to how we're writing down numbers. So using this, I'm going to make one small change to how we represent numbers. I'm going to take this 1,000, 100, 10, and 1, and I'm going to do this. Suddenly, rather than having a tens place, we now have a twos place. Instead of having a hundreds place, we have a fours place. So where did these numbers come from? Well, that 1,000 happened to represent 10 times 10 times 10, or 10 to the third power. That 100 is 10 to the second power. 10 is 10 to the first power, and 1 is 10 to the 0th power. So instead of using 10 as my base and keep doing stuff with that 10, I'm instead going to use 2 as my base. So 2 times 2 is 4. 2 times 2 times 2 is 8, and so on. So let's try counting in binary. So the number 0 is really, really easy to represent. We're just going to represent 0 with a 0. So similarly, if we want to represent the number 1, we can do so. Because we have two digits. We have a 0 and a 1. So that means I can represent the number 1 with just a 1. But now we want to try to represent 2. And that's going to get a little bit tricky, because suddenly we only have two digits, and 2 wasn't one of those digits. So now, in order to represent the number 2, I'm going to do something like this. So we don't have our 0, we have our ones place, and rather than a tens place, we have a twos place. So suddenly, if I have a number like 1, 0, this is actually going to represent the number 2. And why is that? Well, if I have a 1 in the twos place, and I have a 0 in the ones place, that means I have 2 plus 0. And that's going to be equal to 2. So let's jump back. In order now to go from a 2 to a 3, I want to have a 2, and I want to have one more than that 2. So to make that 3, I'm going to need 1, 2, and 1, 1. So the number 3 in binary can be expressed as 1, 1. We have 1 times 2 plus 1 times 1, which is simply saying 2 plus 1, which is 3. So how could we represent the number 4 in binary?
1, 0, 0.
Exactly, so 1, 0, 0. So remember that once we were making the jump from 2 to 3, we needed to make some new digit. So running into the same problem here, both of our digits are already a 1, so we really can't make this number any bigger. So we need to introduce a space for a new digit. And to do that, we can simply say 1, 0, 0. And so this is the number 4. So let's just make sure. If I have 1, 0, 0, that means I have a 4. I don't have any 2s. I don't have any 1s. So that's just equal to the number 4. So let's do one more. So everyone think for a second what 5 in binary is. Don't say it yet. Anyone want to hazard a guess to what 5 is? Yeah, so 101. Exactly. So we don't need a new digit anymore because we have some zeros. So if we just add 1, suddenly we have 1, 4. We don't have any 2s, and we have 1, 1, which added together makes 5. So 5 is 101, or 101 in binary. So rather than counting, let's try somewhat of a bigger number. So here's a binary number, and we want to figure out what this binary number represents in decimal. So to do that, I just want to fill in my table. So I have the 2 to the 0 place, which is 1s, 2s, 4s, 8s, and 16s. So now I can just draw this in. So now it's time for me to convert this sequence of bits to a number. So to do that, all I say is this. I have 116. I don't have any 8s. I have a 4. I have a 2. And I don't have any 1s. So this is the same as saying this. I have 16 plus 0 plus a 4 plus a 2 plus a 0. So if we add this all up, we get the number 22. So that means that that series of zeros and ones represented a 22. So each of these zeros and ones are something that we call a bit. So a bit is essentially the smallest amount of information that we can represent. Right? There's not really anything smaller than we can represent than the difference between 0 and 1. So each of these zeros and ones inside of this binary sequence is called a bit. So very frequently when you're looking at binary numbers, you won't see simply all ones. You might usually see it prefixed with a 0. So rather than writing something like 111, we may write 0111. So notice that adding a 0 to the beginning of a binary number doesn't do anything, right? Because that's just going to be the equivalent of adding 0. So we can add as many zeros as we want to the beginning of a binary number. We're not actually going to change its value. So we're going to take some number, we're going to keep on adding 0, and no matter how hard we try, we're not going to change the value of that binary number. So sometimes you might see a binary number expressed as 011 or 0B111, and that just indicates that this is a binary number. So we know the difference between 111 and the binary representation of that. So let's now try going the other way. So let's say we have some decimal number, and we want the binary representation of it. So the way of going from decimal to binary is much like making change at a cash register. So if you're at a cash register and someone's total comes to $20.50, and they give you $21, you want to make change for that using as few coins as you possibly can. So not only do you not want to aggravate your customer by giving them 50 pennies, you also don't want to aggravate your manager, who doesn't want you to give away all of the pennies the cash register has. So you want to be as conservative as you can. So at any opportunity, you want to use the largest coin you possibly can. Right? If I need to make change for 51 cents, and I can use 2 quarters, I want to use as many quarters as I possibly can, until suddenly giving one more quarter will be giving them too much change, which is arguably worse. So let's say we have a number like this. We have the number 14. And we say, what is the binary representation of this number? So what we want to do is start off with the same little table that we started off with before. So we have the 1s, 2s, 4s, etc. places. So let's start all the way to the left. So if we start in the 16s place, if we put a 1 there, then suddenly we've given someone 16 cents when they've asked for 14. That's already way too much. And there's nothing we can do later to take that money away. So that means we really shouldn't put a 1 in this first place because we know that our answer cannot be right. So that means the first number here is going to be a 0. OK, so let's move on to the next place. So now we have 8. So we have a coin that represents 8 cents. And we're trying to make 14 cents. So if I give you an 8-cent coin, that's not going to be too much. And I know that I want to be as conservative as possible. I don't want to give you more coins than I have to. So if I can give you an 8-cent coin, I'm going to. So that means that in this place, we want this to be a 1, because we want to use this slot if we possibly can. So now we had our number 14, and we just gave away 8 cents. So that means we have to make 6. So moving on to our next place, we have 2 to the 2, which is 4. So if I'm trying to make 6 cents, and I have a 4-cent coin, that's good, because that means that I can give you a 4-cent coin. I'm not going to give you too much. So we want to put a 1 right there. So that means that we've given you 12 cents so far, which means we need to give you 2 more cents. Well, right now I'm at the 2's place. So if I give you that 2 cents, that means that suddenly I've given you all of the change that I have to give you. So that means I don't want to give you anything from the 1's place because you're already done, which means that this can be a 0. So any questions on how we just did that? Yeah?
You said that you had 4 cents left to give, and you were able to do that on the right-hand side where it says 2, 1, 1 right there. How did you get to having the 2 cents left, I guess, is my question.
Sure. So let's start here. So right now we have 2 to the 3, and that's going to be 8. Right? So we have 14 minus 8, and that's going to leave us with 6. So now we're at 2 to the 2, and that's 4. So we went from 6 cents. Now we can give you 4 more. Now you have 2 cents left. So now we're at 2 to the 1, and now we can give you 2 cents. So we've given you all of your change. So at each step, we basically subtracted how many cents we just gave you based on whether or not we put a 1 or a 0 in that place. So now if we take this binary sequence here and we try to convert back, we know we have 8 plus 4 is 12, plus 2 is 14, plus 0 is still 14. Other questions? OK. So let's try something else. Let's try adding up 2 binary numbers. So let's say we have these 2 binary numbers here, and we want to compute the sum. So one naive way to do this would be to figure out, all right, well, what's this value in decimal? What's this value in decimal? Question first? Sure.
When you put the 0 in the last one, do you have to do that as like a placeholder? Or could you just leave it as 0, 1, 1, 1?
Sure. So in our example here, do we have to put this 0 all the way to the right as a placeholder? So in this case, we do. Right? If we didn't have a 0 here, that would mean that the first digit was a 1. And suddenly, rather than being the 2's place, that's now the 1's place. So if we drop this 0, suddenly this is a different number. On the other hand, all the way to the left, that's a different story. Yeah, we do not need that, because all this number on the left is doing is it's just saying, I'm going to add 0 to my total. So so we can add as many as we want on the left, but not as many as we want on the right. Questions? OK. So let's add these 2 numbers together. So luckily, we can add binary numbers in really the same way that we're used to adding decimal numbers. So first, we can start off with an easy one. We'll start all the way to the right, just like we did in grade school. So 1 plus 0 is 1. So we can really easily fill in the value 1 here. So the next one's a little more challenging. What is 1 plus 1? 2. So 1 plus 1 is 2. And how do we represent a 2 in binary? 1, 0, exactly. So if this were grade school and suddenly these 2 values added up to something like 10 or 23, remember what we do? What do? Yeah, we have to carry the 1. So we have 1 plus 1 is 2. So I'm going to write down a 0 carry the 1. So suddenly now we're in our next spot. We have 1 plus 1 again. So what do? 0 and carry the 1. So finally, we're left with an easy one. What's this? What's my first digit now? 1, exactly. So we have 1 plus 0, which is 1. So this is the sum of those 2 binary numbers. Make sense? Yeah?
Can you explain the third column again?
Sure. So what we did is we said 1 plus 0 is 1. So in the second column, we had to say 1 plus 1 is 2. So in binary, that's like saying it is a 0, carry the 1. So suddenly we carried this 1. We want to add that on to the next column now. So suddenly,
Are you saying like 2 to the power of 1? Is that what you're saying? Or
right.
2 to the power of 0?
So we're saying that 1 plus 1 is equal to 2 to the power of 1, because that's 2. So normally we'd express the number 2 with just a 1 followed by a 0. So we're just kind of doing that here. We wrote down a 0, and now we carry the 1. Just like when we regularly add, we can, if we have the number 12, we write down the 2, and we carry the 1. And so it works the same way in binary, even though it looks a little bit different. Other questions on how we got here? OK. So now, hopefully jokes like this can make some more sense. So the joke here is there are 10 types of people. 10 in binary is what number? 2. So there are really 2 types of people. If you're groaning because you've already heard this before, we have the more sarcastic. There are 10 types of people, those who know binary and those who have friends.